I'm going to run through one final example of the limit comparison test. Did one on an earlier video. And you can see I've written out a couple of terms of a series here. Notice again, and I did this in the last video as well, instead of having sixes in each of the numerators, I actually have ones. That's because you can always factor a constant out of a series. So I'm going to factor the 6 out to leave me just a 1 in the numerator, because again, 6 times some convergent value will still be something that's convergent. 6 times infinity would still give me infinity and would still diverge. So you can always factor out a constant. All right, so this one, I see an n in the denominator, and I'm thinking, oh, I want to do a comparison to 1 over n, which of course is the harmonic series. And you can start substituting some values in here, and you get 1 over 1 plus 1 over 2 plus 1 over 3, and so on. And of course, you can see there that that looks a whole lot like a harmonic, and the top series looks a whole lot like a harmonic as well. There's one problem, though. The harmonic series is divergent. Okay, if I'm going to use the comparison test, the series that I'm trying to determine whether or not converges or diverges needs to have terms that are greater than the terms of the divergent series. Okay, because if I have this divergent series and the terms add up to infinity, and I have terms that add up to something bigger than that, it's also going to add up to infinity. Well, here's the problem. 1/2 is smaller than 1. 1/3 is smaller than 1/2. 1/4 is smaller than 1/3. And so as a result, I can't do a comparison test here because I think it's going to be divergent, but I don't have terms that are greater than or equal to the terms of the divergent series, okay? And this is where the limit comparison test comes in. It says if you can't get all of your terms less than or greater than, whichever way you need for divergence or convergence, you can look at the ratio of the two series as you go out to infinity. Okay, and it doesn't matter. You can take it doesn't matter which one you do in which place, but we're looking at the limit as n approaches infinity of the ratio between the two series. So I can do 1 over n plus 1, and I can do 1 over n. Okay, remember, dividing by a fraction is the same thing as multiplying by the reciprocal. So that's the same thing. Dividing by 1 over n is the same thing as multiplying by n over 1. Okay, and anyway, so the limit here ends up being the limit of n over n plus 1. Okay, and you can see as n approaches infinity, the 1 is going to become increasingly unimportant. It's going to end up approaching 1. And by the way, even if you hadn't factored out the 6, even if you had made this 6 over n plus 1 and 6 over n plus 1, you would have ended up with 6n over n plus 1, which would have approached a limit of 6. 6 is still a constant. Okay, and all it's saying is that series on top, as you go farther and farther out, the individual terms in general are going to be about 6 times as big as the terms of the lower series. Okay, in other words, one is a multiple of the other. Whatever one series does, the other one is also going to do, as long as you get a constant value. So it can be 1, it can be a half, it can be a fourth. What you don't want is infinity or 0 or something like that, because that would suggest that one of the two series is overriding the other one, and you're ending up with one that is behaving very differently. But anyway, as long as you get a constant as you go to infinity, they both behave the same way. So 1 over n is divergent. That means 1 over n plus 1 is also going to be divergent.